If you look at modern breach reports, you will notice a pattern. Attackers are no longer only exploiting exposed servers or weak passwords. They are targeting software supply chains, compromised dependencies, CI/CD pipelines, misconfigured containers, insecure APIs. Your applications are now the primary attack surface. And in a digital-first enterprise, applications are the business. If your application layer fails, customer trust collapses. If your pipeline is compromised, every release becomes suspect. If your software supply chain is poisoned, the impact multiplies at scale. As an enterprise security architect, you must treat application and DevSecOps security as architectural domains, not as developer checklist. You are not simply protecting code, you are protecting business continuity. Secure software development lifecycle, secure SDLC, is not about adding a security review at the end of development. It is about embedding security thinking from ideation to deployment. You must design an SDLC model where security is integrated into requirements gathering, architecture design, development standards, code reviews, testing, release processes, post-deployment monitoring. If security is introduced only before release, defects become expensive. If security is embedded early, vulnerabilities are reduced systematically. As an architect, you must define secure coding standards, threat modeling expectations, security review gates, approval checkpoints, documentation requirements. Secure SDLC is governance through design. It ensures that security is not optional. It becomes part of the delivery rhythm. One of the most powerful practices in secure SDLC is threat modeling. Before code is written, you evaluate. What are the trust boundaries? What data flows exist? What external interfaces are exposed? What misuse cases are possible? What high-value assets require additional protection? Threat modeling shifts security left. Instead of reacting to vulnerabilities later, you anticipate architectural weaknesses early. For example, if you are designing an API exposed to partners, you evaluate authentication model, rate limiting, input validation, data exposure, logging integration. This reduces redesign costs later. As an architect, you must institutionalize threat modeling as a mandatory practice for high-risk systems. Modern enterprises deploy software continuously. CI/CD pipelines automate build, test, and release processes. But pipelines themselves have become attack targets. If an attacker compromises your CI/CD system, they can inject malicious code into trusted releases. Therefore, you must architect security into pipelines. CI/CD security controls should include hardened build environments, restricted runner permissions, least privilege access for pipeline identities, secure secret management, code integrity verification, approval gates for production releases. For example, instead of embedding credentials in scripts, you use secure secret stores. Instead of allowing broad admin permissions to pipeline accounts, you define scoped roles. Pipeline runtime environments should be monitored. Execution logs should be centralized. Outbound access from build runners should be controlled. The pipeline is part of your supply chain. If the pipeline is compromised, everything downstream is compromised. Architecturally, it must be treated as a high-value asset. Security testing must be automated and integrated into the development lifecycle. You must design a layered testing strategy. Static application security testing, SAST, analyzes source code for vulnerabilities before execution. Dynamic application security testing, DAST, evaluates running applications for exploitable flaws. Software composition analysis, SCA, identifies vulnerable open source dependencies. These tools serve different purposes. SAST helps detect coding flaws early. DAST validates runtime exposure. SCA addresses supply chain risk. As an architect, you must define when testing occurs, what severity thresholds block releases, how false positives are handled, how vulnerability remediation is tracked. Testing must not be optional, it must be integrated into CI/CD pipelines automatically. If testing is manual, it will be bypassed. If testing is automated and enforced, it becomes part of delivery culture. Modern applications depend heavily on open source components. Each dependency introduces potential risk. You must design supply chain security controls that address dependency inventory, vulnerability scanning, approved repository usage, version pinning, code integrity verification. Supply chain security is about trust validation. You must verify where components originate, whether they are tampered, whether they contain known vulnerabilities. Architecturally, this means restricting external package sources, monitoring dependency updates, enforcing integrity validation during builds, maintaining visibility across all deployed artifacts. Supply chain compromise has become a preferred attack vector because it scales. If you compromise one dependency, you may impact thousands of systems. Your architecture must assume supply chain risk and design mitigation accordingly. Security does not stop at code scanning. You must monitor pipelines while they execute. Pipeline runtime security includes detecting abnormal execution patterns, monitoring unauthorized configuration changes, logging privileged pipeline actions, restricting environment variable exposure, controlling artifact storage access. For example, if a pipeline suddenly modifies deployment scripts outside approved processes, that event should trigger investigation. Runtime visibility transforms CI/CD from a black box into an auditable process. As an architect, you must ensure pipeline logs integrate into enterprise SIEM. Alerts are generated for suspicious activity. Access reviews are conducted for pipeline administrators. Pipeline security must be governed at the same level as production systems. A software bill of materials, SBOM, provides a structured inventory of components used within an application. SBOM enables dependency transparency, vulnerability impact analysis, compliance verification, rapid response to newly discovered vulnerabilities. For example, if a critical vulnerability is announced in a common library, an SBOM allows you to quickly identify which applications are affected. Without SBOM, impact analysis becomes guesswork. Integrity validation ensures that artifacts deployed to production match approved builds. This includes artifact signing, hash verification, controlled artifact repositories, release approval workflows. Integrity validation prevents unauthorized modification of build artifacts. SBOM and integrity controls together strengthen trust in your software supply chain. DevSecOps is not a development initiative alone. It is an enterprise architectural capability. You must ensure CI/CD integrates with identity governance. Logging integrates with SOC monitoring. Vulnerability data integrates with risk management. Release policies align with compliance requirements. Application and pipeline security must connect to broader enterprise security architecture. Fragmentation creates blind spots. Integration creates resilience. As an enterprise security architect, your responsibility is to align DevSecOps with identity, network, cloud, and governance domains. Executives may not understand SAST or SBOM details. They understand risk exposure. You must translate technical controls into business impact. Instead of saying, "We implemented SCA," say, "We reduced the risk of deploying vulnerable third-party components into production." Instead of saying, "We hardened our pipeline," say, "We strengthened the integrity of our software releases to prevent supply chain compromise." Executive alignment ensures sustained investment. DevSecOps requires collaboration. Developers must see security as an enabler. Security teams must avoid becoming gatekeepers. Operations must integrate monitoring seamlessly. You must foster a culture where security findings are addressed proactively. Vulnerability remediation is prioritized. Security testing is normalized. Pipeline governance is respected. Cultural maturity determines long-term success. Tools alone do not create DevSecOps. Architecture and leadership do. Ask yourself, is security embedded in your development lifecycle or added at the end? Are pipelines hardened and monitored? Do you know what dependencies your applications use? Can you verify artifact integrity before production deployment? Is supply chain risk managed architecturally? Application and DevSecOps security architecture determines whether your digital transformation is secure or fragile. In a software-defined world, application integrity equals enterprise integrity. If this lecture helped you understand how to secure the software supply chain architecturally, make sure you subscribe to this series. In the next lecture, you will explore data security architecture and how to protect information across its lifecycle. Like this video if you found it valuable. Comment below and tell me, does your organization treat DevSecOps as a technical initiative or as an enterprise architectural capability? Your journey toward mastering enterprise security architecture continues in the next session.